Hello everyone, and welcome to the lecture on op amps. We're going to cover the basics of op amps as well as their role in using feedback to regulate systems or just as a comparator or amplifier. So what is an op amp? It's a device constructed of several transistors and diodes, and the exact configuration of those transistors and diodes varies with the model, but they all share very similar properties. So we're just going to go over the general properties, and then later on, if needed, you can modify them to match the exact configuration that you need. At its core, an op amp is a differential amplifier. And that means that it takes the difference between two inputs and then sends an output that is some function of that difference, usually a multiple. And this gives the op amp all kinds of uses. They can be used as comparators, where two inputs are compared to each other and the output tells us which value is higher. They can be used in positive or negative feedback applications, which we're going to go over in some detail during this lecture. And they can also be used as an amplifier, which makes a small signal larger, which is where they get their name from, operational amplifier. And with that, let's look at some basic properties. First, the basics. They are a 5-lead component. Oftentimes you'll see symbols which have only 3 leads, but this is just implying the source leads, which are still present in the real thing. We're just implying them for a cleaner diagram. What are these leads? The V plus and V minus on the left half of the symbol are the input terminals, where the plus corresponds to the non-inverting terminal and the minus corresponds to the inverting terminal. And why this is going to become clear in a little bit. Vs plus and Vs minus are the power supply terminals, which determine the maximum or minimum output from the voltage out, labeled by V out. So one of the consequences of the makeup of the interior of an op amp is that the op amp tries its best to reduce the difference between the two inputs back to 0 using output. But before we go into that and how that plays back into feedback, we're going to go over some basic properties for the outputs and inputs of each terminal. The first is that the output voltage is a multiple of the difference between the two inputs. The multiple is called the gain, denoted by that A, and an ideal op amp will have a gain of infinity. Real op amps have gains that are quite high. 50 or 60,000 is not uncommon, but still not infinity. The second property that we need is the input resistance. Ideally, the current reaches the input terminals and then stops. None of the current makes it into the op amp, giving an input resistance a value of infinity. The only thing that happens when current reaches the op amp is that it can tell how much voltage it has. Of course, this is not true, but input resistance is still very, very high, and we can often just take it to be infinity as long as our applications we're using our op amp for are not very sensitive. And in a similar vein, the output resistance is taken to be 0. And this means that voltage does not drop once it leaves the op amp until it hits another component. If we calculate a 5 voltage output, then our output is 5 volts until it hits something else. In real life, this is not quite true. Our calculation that we get, our 5 volts, is going to have some small drop off that is not taken care of in terms of the ideal op amp. Now it's very small, so we can often just take the output resistance to be 0. So these properties are vital in analyzing op amp circuits, as well as troubleshooting and any issues that might come up in constructing or analyzing our circuit. So let's look now at a couple of different configurations of an op amp. We're going to look at the open loop gain. We're going to look at inverting and non-inverting operational amplifiers. And then we're also going to look at the Schmitt trigger, which is a positive feedback trigger. So first, open loop gain. Open loop gain is the characteristics of an op amp that's not experiencing any kind of feedback. All 5 terminals are independent of all other 5. They're not at all hooked up into each other. In this situation, the output is determined simply by the voltage loop gain A. So let's take a look at the real case of the output, where VO is the y-axis, or the output, and V plus is the input to the non-inverting terminal. And we're taking the inverting terminal input to be ground or 0 volts reference. This real case shows us that there is a small area of input voltage where the op-amp is not in saturation, where saturation is defined to be the output is either at Vs plus or Vs minus, which once again are the limits of our output. This region is determined by the value of gain, and the slope until we reach our saturation voltage from 0 is determined by Vd plus or Vd minus, where those are equal to Vs plus over A or Vs minus over A, which gives us our slope. So if we have a very small a, that Vd plus or minus gets pushed out, and we have a wider range where we're not in saturation. But we often have a very, very high gain, or A, so these slopes and regions are very, very small. And if our gain is in fact infinite, they become 0. So we wind up with what turns out to be a step function, where as long as if our input on our non-inverting terminal is above 0, we are at saturation, and if it's below 0, we are at saturation in the negative side. And now we can also shift this around by a couple of basic rules that should be pretty familiar to anyone who remembers how to shift functions around. We can move our plot up or down by changing our source voltages up or down. So if Vs plus is much, much higher, we would have a higher saturation voltage. And if we shift our Vs minus so that it's above 0 but still below Vs plus, then our entire op-amp would operate above 0 volts for output. And we can shift left or right by changing our reference voltage, which in this case is our inverting amplifier, V minus, away from 0. So 0, or wherever the reference voltage is, gives us the point on our x-axis where we're going to cross over. So we can see right away this might be useful. If our inverting input is an important value that we would want to check our non-inverting input against, our op-amp output is at negative saturation, or the Vs minus, so long as our V plus, our non-inverting input, is below it. But as soon as our non-inverting input reaches this important value given by V reference, it switches to the positive saturation, which creates the comparator. So this is a pretty simple one, the simplest case where we don't need to do any kind of real math. We just kind of look at the characteristics and see what's going on. But now we're going to look at some feedback, which does have some math involved. Now there are two kinds of feedback, positive feedback and negative feedback. And we're going to limit our discussion of these to op-amps, since there are entire courses on feedback. Positive feedback feeds our voltage out back into the non-inverting input, or V plus. And this tends to create a situation called hysteresis. And hysteresis is where once a system is in one state, it stays there. And if it's in the other state, it stays there. So basically, it's pushing our system to extreme values. And in the case of an op-amp, it's pushing our output to Vs plus, where it will stay, or Vs minus, where it will stay, unless we give it some significant input changes. And this is a good thing for systems which are experiencing a really noisy input, as it can smooth the output signal. Negative feedback occurs when the output of our op-amp is fed back into the inverting input. In this situation, things tend to settle toward an equilibrium somewhere between the two extreme states. And this is incredibly common in every field. For an example, just look at predator-prey relationships. Predators and prey settle into an equilibrium through negative feedback. And you can examine the Locke-Volterra equations for this, where you reach an equilibrium where the system is not only predator or only prey. You reach some kind of equilibrium between the two. And that is a result of negative feedback and negative feedback helps keeps things from spiraling way out of control. So to illustrate these as far as op-amps are concerned, we're going to analyze some simple op-amp circuits using both kinds of feedback, the first two of which are going to be utilizing negative feedback. This particular circuit is called a non-inverting amplifier. Non-inverting in this case because the sign on the output matches the input, positive output. We're going to assume for all of these cases that our source voltages, Vs plus and Vs minus, are sufficiently high or low that we don't have any issues with clipping arising there. So the basic setup of this one is that the non-inverting input is our signal that we're measuring, that we're taking into account. The op-amp is going to do its thing, and then a portion of the output is fed back into the non-inverting input, V minus, through a voltage divider. And our task is to determine the output, VO. First thing, we're going to use the voltage divider to determine the inverting input relative to output. And the non-inverting input is the signal and independent of everything else. And the reason we're feeding it back into the negative is one, not only because it's negative feedback, but because remember the op-amp tries to get the voltage difference between the positive and negative terminals to be equal to 0 by modulating the output. So using the voltage divider here helps us regulate that so that we don't actually get back to 0 because we want to have some output. So first thing, V minus equal to voltage divider equation utilizing VO. And then we're going to use the op-amp gain relationship between the inputs to construct a relationship between all three. VO equals A, V plus minus V naught. And we're going to sub in our equation for V naught that we got. Then we're going to solve for V out. It's going to get a little messy, but we can get there. And then we're going to need to simplify this as much as possible. After our simplifications, we see that V out is equal to V plus times a complicated relationship between gain and the voltage divider equation. So let's look at that a little more closely. And we're going to take into account our assumption of ideal amplifiers that our amplification factor A, or gain, is equal to infinity. As A approaches infinity, our equation is going to simplify to V naught equals our input signal times the quantity 1 plus the ratio of R2 over R1. So we can see from here, the smallest possible output is the same as our input, and the largest is infinity, assuming we can find an infinite ratio between two resistors. And the other thing we can see is that this is a stable result. Even if our gain is not infinite, we're going to reach a simple multiple of our input, and it's going to stay there. Well, it's going to oscillate with input, but only with input. There are no other effects happening. The only thing that will change the output is a change in the input. So this is stable, negative feedback. Now for the next one, which is the inverting amplifier, where in this case, we're going to have a negative output given a positive input, or a positive output given a negative input. So that's why it's inverting. And the other big difference is that our input is going to be given through the inverting input. And we're now going to try to find the output voltage using that feedback, because our reference signal is on our inverting input and our feedback is through our inverting input. Our voltage plus, or our non-inverting input, we're going to take to just be 0 or ground. And just like before, we're going to use our op-amp relationships, and we're going to start with the non-inverting input because it's equal to 0, and 0 is nice and simple to work with. And then the inverting input, which is a little bit more complicated because there are two sources feeding it. The first is our signal voltage, VI, and the other one is our VO. Both of them have an impact on our inverting input. And we're first going to determine that our signal voltage feeds into our inverting input via a voltage divider equation between the two resistors. The other input, shown by the green arrows, takes the voltage output and feeds it into the inverting input. Also feeds through a voltage divider but this time from the other direction because it's the same one. So once we have these, we can substitute them into our op-amp relationship. We're going to once again have to solve for voltage out, which is a little bit messy, but we can do it, and we can find this complicated relationship. We're going to simplify a little bit more again. And then we're going to see that we have a negative value output and a similar kind of fraction to what we had for our non-inverting amplifier, where once again, if we take A to approach infinity, our relationship becomes very simple. V out is equal to negative V in times R2 over R1. So this is two examples of negative feedback where we take our input and our output reaches some kind of equilibrium proportional to the input. We aren't necessarily reaching our Vs plus or Vs minus unless our ratios become so high that we do, but we will reach an equilibrium. And if we do reach our extreme outputs, it's only by virtue of our source voltage not being high enough. So now we're going to look at positive feedback and why it might sometimes be useful where we stay at our extreme states. This circuit is called a Schmitt trigger, and the Schmitt trigger takes advantage of positive feedback and hysteresis to smooth our inputs into a constant or relatively constant output. So as a result of the positive feedback and hysteresis, there is a range of inputs which do not result in a change of output. And this is called the immunity band, and we're about to determine the immunity band. The first step is to determine the input to the non-inverting terminal, which should look familiar because it's once again a voltage divider, which should be second nature at this point. And once more, we're going to use the op-amp relationships where we're going to assume an initial state where our output is equal to our positive source voltage. And from here, from this relationship, we can see that as long as the input to the inverting terminal is less than that of the source voltage, which is moderated by the voltage divider, the output will remain in the high state. Remember that the ideal op-amp is a step function where any input to the non-inverting terminal greater than that of the inverting terminal results in the output being as high as possible. So we're in our high maximum state, which means that fluctuations, so long as they do not result in Vi becoming greater than our positive terminal input, mean that our op-amp output remains at the high Vs plus state. Now, if we start with the opposite assumption, where the output is initially in the low state, we could find a similar value where the Vi remains above. Our output will not change. So now we have a high value and a low value. If we stay lower than the high value, we're not going to change, and if we stay higher than the low value, we're not going to change also. So let's illustrate that with a voltage plot similar to what we saw before, and we're going to assume an ideal op-amp here, because things get a little messy when it's non-ideal, because now you have like a quadrilateral kind of situation going on. So let's start with the green, where we're starting in the high state. As long as our voltage input stays below the VL signal range, it will remain in a high state. And then after that, it will go low. And then the blue line, where we start low, as long as our input signal remains above that VH value, it will remain low. And then once it hits it, it's going to go high. So we have this square box kind of thing in the middle of our voltage plot. And within that is our immunity band. Our Vi in between VH and VL does not change the output of our system. It's immune to change. That's why it's called immunity band. Now this is useful. It's used in all kinds of things. Like a common place to find a Schmitt trigger is in a fire alarm system, where we take noisy inputs, and we don't want to have the fire alarm go off every second because there's little particulates in the air or what have you that may affect the input signal. So we want to have a range of values where a little bit of noise isn't going to make everyone lose sleep. So we use the Schmidt trigger with an immunity band so that the fire alarm stays off unless the output changes so much that it must be a fire going on. So op amps have a bunch more uses. These are the basics, and we're going to be using some of these properties in some of our labs coming up, especially a lab coming up with the Arduino, which is going to be a temperature regulator, which is going to utilize feedback and an op amp as a comparator to determine whether or not to turn on a heat generating component. Don't forget the exam that's coming up next week. I will be providing a set of practice problems and topics, and then I'll probably be doing a couple of example problems live during my office hours this week, which is Thursday and Friday, 12 to 1. Other than that, good luck on the exam. Until next time.